All right, so we're going to undo everything that we just did. So remember, if we have any constant raised to a power containing a variable, then the integral will be 1 over the natural log of a times a to the k plus c. So knowing that, we have number 10 is the integral of 3 to the x power dx. Remember, you cannot do power rule on this because your variable's in the exponent. So what is your u? My u is x. What's your du? My du is 1 dx. So I've got everything I need. I just have to turn around and use this formula. So I'll have 1 over the natural log of the base. Okay, so 1 over the natural log of the base, a to the u, which is 3 to the x, plus c. Okay, so, and that's it. You're done. All right, so let's do another one. I've got the integral of 4 raised to the sine x times cosine x dx. So what's your u? Well, your u is going to be up in the exponent. Okay, so if my u is sine x, what's my du? It's cosine x dx, which I have. Okay, so this is already set up as a to the u du. So the integral is going to be a to the u plus c. And done. So again, how do you check to make sure oh, I lied. Over the natural log of 4. Holy cow, I'm glad I did that. All right. So how do I check my work? To take the derivative of an a to the u, you write what's sitting there, times the derivative of your exponent, which is your cosine x dx, times the natural log of 4. Okay, so you've got it all. You got this back with the way that you're doing that. All right, so we have, hang on. All right, number 12 is, so I'm going to integrate, and I'm going to use limits of integration. So I'm going to go from 1 to 3 of 5 raised to the x minus 3 raised to the x dx. So I've got two separate terms. As long as I've got the derivative of my exponent, then everything is balanced. Okay, so the derivative of my exponent is 1, and that is 1 dx. So I've got that. This one is the derivative of my exponent is 1 dx, and I've got that. So I just need to integrate. So the integral is going to be 1 over the natural log of the base, which in the first case is going to be 5, natural log of 5, times 5 raised to the x power. Okay, minus, do it again, 3 raised to the x power over the natural log of 3. And we're going to evaluate at 3 and 1. So if I evaluate at 3's, 5 raised to the third power is 125. Minus 3 raised to the third power is going to be 27. And then minus 5 raised to the first is 5. Minus 3 raised to the first is 3. So if you'll notice, you've got some like terms. I have 125 of these minus 5 of these is 120 natural log of 5. And then a negative 27 minus a negative 3 is going to be a negative 27 plus 3. So I've got negative 24 over the natural log of 3. And that's your exact answer. What else do I have? Flip. All right, I've got 2 raised to the negative x power. So 2 raised to the negative x power. So what's your u? My u is negative x. So my du is a negative 1 dx. So I need a negative, balance with a negative. And now this is of the form a to the u du. So this negative is going to come along for the ride. And then I have times what's sitting there, or your a to the u, which is a 2 to the negative x, over the natural log of u. So that's the natural log of 2. Plus a big old c. Okay? And then we have finding an equation of a tangent line to the graph of the function at the given point. So this one's going to be a little bit more exciting. I've got a y equals x raised to the sine x power. Okay, so when I set this up, I can integrate both sides. And I want the equation, oh, that is such a lie. I want the equation of the tangent line. Land of Goshen. So I got a pi over 2, comma, pi over 2. I am not integrating, people. I am differentiating because I want the slope of the tangent line. So I'm going to have to do logarithmic differentiation. How do I know that? Because I've got an x here and an x in my exponent. So my formula for slope is going to be found by taking the log of both sides. And now I can drop that exponent out front as a coefficient. Okay, so I've got the natural log of y equals the sine of x times the natural log of x. And now I'm set up to where I can take derivatives. So what is the derivative of a natural log? It's the derivative of the argument over the argument itself, dy, equals, I'm going to have to do product rule here, and everything is going to generate a dx, so I'm just going to write my dx at the end. So I've got the first, which is sine x, times the derivative of the second, which is going to be a 1 over x, okay, plus the second, times the derivative of the first, which is cosine, and then each one of those had a dx that I pulled out. So divide both sides by dx, and then multiply both sides by y. So I have sine x over x plus the cosine of x times the natural log of x times y. Well, what was y? Y is x to the sine x power. Okay, so that is your formula for slope, and I want the slope of the tangent line, which means I'm going to evaluate it at x. And again, honestly, you didn't have to turn around. You could have put y here after you evaluated it, but I'm just going to stay the same the whole way through. So my value for slope is, I'm going to evaluate at a pi over 2. So I've got the sine of pi over 2 over pi over 2, okay, plus the cosine of pi over 2 times the natural log of pi over 2. And all of that is multiplied by the pi over 2 raised to the sine of pi over 2. And this is actually a whole lot prettier than what you think. What is the sine of pi over 2? It's 1. So 1 over pi over 2 means I'm going to flip and multiply. Okay, you can't see. So that's going to, this turns into a 2 over pi. So 2, so I have a 2 over a pi. Cosine of pi over 2 is 0. So this is gone. Okay, and then I have pi over 2 raised to the sine of pi over 2. Well, what's the sine of pi over 2? It's 1. And so I got 2 over pi times pi over 2, which means everything reduces, so my slope is 1. Okay, your slope is 1. Well, now I can find the equation of the tangent line. So if I'm looking for the equation of the tangent line, I've got a y equals mx plus b. So y equals mx plus b. So my y is pi over 2. My m is 1. My x is pi over 2 plus b. So I've got pi over 2 equals pi over 2 plus b. When I subtract pi over 2 from both sides, I get 0. So your y-intercept is 0, which means the equation of the tangent line is simply y over x. Okay, and finally, we have the last one. So find the area of the region bounded by the graphs of the equations. So I've got a y equals 5 raised to the x power. I've got y equals 0, which means nothing under the axis. I've got x equals 0, and I've got x equals 2. Okay, so those are your limits of integration, because we're in terms of x. So I'm going to go from 0 to 2 of 5 raised to the x power dx. So my u is x, which is going to have a derivative of 1 dx. So I'm done. I don't need to balance anything. And then what is the integral of an a to the u? It is 1 over a, the natural log of a, goodness. 1 over the natural log of your base, times what's sitting there, which is going to be a 5 raised to the x power, and then plus c. Okay, so I'm going to simplify this a little bit. So I've got a 5 over x, or 5 raised to the x over the natural log of 5, and I'm going to evaluate that from 0 to 2. So if I shove in a 2, what is 2 squared? It's 25 over the natural log of 5 minus, if I shove in a 0, any number to the 0 power is 1, so I get minus 1 over the natural log of 5. Well, 25 of these minus 1 of these is 24 of these. So that is the evaluation, and that's the area under that curve.